Hi, so today we're going to take a look at part 2 of our log word applications. In part 1, we took a look at compound interest and continuous compound interest, and today we're going to take a look at some growth and decay questions. So let's jump right into some examples. So basically, when you have growth, your base would be something that would have a value of larger than 1. If 1 is a neutral number, anything larger than 1 would give you some form of growth. Anything between 0 and 1 as a base would give you something in which you have some form of decay. And when that's taken exponentially, then that can either decay really rapidly or grow really rapidly. So here's an example. Mr. Wong just bought a venti coffee from Starbucks. The amount of caffeine in his bloodstream decreases by 13% each hour. Write an equation representing the percent P of caffeine left in his body after n hours. So you could say something like this. P is equal to, well, I guess you could say PO, and that's basically saying what your original amount is. And it decreases by 13% each hour. So this is what you start with, similar to our principal in our compound interest formula, and this is what you end with. And then in the bracket here, our base is going to be 1 subtract 0.13. And if you wanted to, you could just write 0.87 right away, but it's a decay question because you're losing 13%. So we need to subtract 13% from our regular neutral number 1. And we're going to do that for n hours. And so that would be our equation to represent it. So after 1 hour, you'd be left with 87%. Well, after 2 hours, you would have 87% times 87%. After 3 hours, you would have 87% times 87% times 87%. Or another way of being able to say that would be 0.87 to the power of 3. So what would happen after 4 hours? Well, after 4 hours, you could say something like this. Imagine you start with 100%. That's all the caffeine. Sounds great. You could say that would be to the power of 0.7 to the power of 4. So that would happen after 4 hours. This is what would end up happening from it. And you could say 0.87 to the power of 4 would say that we would be left with approximately, let's just go to the nearest percent, 57% of the caffeine would still be left in our system. So think about what happens when, if you have a coffee or you have something with a lot of caffeine in it, after 4 hours, you still have parts of that caffeine in your system. How long would it take to have only 25% of the caffeine remaining? Okay, so if you think about something like that, you could say, well, if P equals PO 0.87 to the power of n, you want only 25% to remain of the 100%, your start and end amount. Your base is 0.87, and it's being raised to the power of n. And so then if you divide by 100, you'd be left with 0.25 is equal to 0.87 to the power of n. And we need to take the log of both sides. So I'm just going to do this up here. And we could say something like log of 0.87. So if you say something like that, that's your base of 0.25 equals n. You could have also logged to both sides and kicked the n in front if you want. And if you do something like that and you put it into your calculator, let's see what you get. So you'd have log. And so if you do that, you should get something where n is going to equal 9.95 hours. It didn't say what to round it to. You could maybe say 10 hours or something like that, but that's what you get. Okay, example number 7. So here's a question about population, and in Alberta, this represents what happened in Alberta since 1981, where your starting population, your PO right here is 2.28 million, where P is measured in millions, so it can just say 2.28. And you can actually tell that its growth rate is 1.4% because 1 is neutral and it's gone up by 1.4%. And it's going to do that for N years since 1981. So this is probably going to be something that we could compare with what's happening in Alberta in the year 2020. We should take a look at that. Assume that this pattern continues. Determine when the population of Alberta might become 4 million. So your end population is going to be 4, which means your p-value is going to be 4. So 4 equals 2.28 times 1.014 to the power of n. We could divide by both sides by 2.28. And then based off of that, you could say something like this. I know that that number is a decimal, is not the cleanest number to write. It's like 1.75 something. So it equals 1.014 to the power of n. We could rewrite this as a log. You could say log of 1.014 of 4 over 2.28 equals n. And we could put that in our calculator. Again, if you wanted to, you could log both sides, soccer kick the n in front, and solve that just exactly the same way. And that's also a very good way of being able to do this. And if you do this, you get n equals 40.4 years. Well, what's happening? Let's see. Determine when the population of Alberta might become 4 million. Well, if that was years since 1981, then this would be in the year 2021.4. So sometime in the year 2021, it's going to reach 4 million. I'm curious what the population of Alberta is right now. We should look that up and see what they say. Okay. Example number 8. In 1995, I feel like we got to update these questions, and we're talking about a long time ago. In 1995, Canada's population was 29.6 million, and it was growing at a rate of about 1.24% per year. Estimate the doubling time for Canada's population growth. Okay, so now we get to make up an equation. Our starting amount is 29.6 million, and that's our and we're growing at a rate of 1.24%. So 0.0124, and it's being raised to the power of, we don't know, we could say to the power of t for time in years. And they want it to double. So we need double of 29.6 would be 59.2. We could put that right here. And if you want to use a 2-to-1 ratio instead, you could do that, but this kind of illustrates what we're looking for. And so based off of this, I just want to clarify that all of these questions here are now talking about annual growth. And so because it's annual growth, if you're thinking, well, with compound interest, we always divided it by the number of times we compound per year. But for these questions, they don't compound frequently. That's more done in things like for investments. This is rather talking about what would happen for annual growth rate. So based off of that, we could divide both sides by 29.6. We know we're going to get a 1-to-2 ratio. We could log both sides, and we could say something like log of base 1.0, or we could log both sides, or we could put into log form, which I think is probably a little bit easier. And we get something like this, so let's calculate that. And we get something like 56.2 years. hey, remember we talked last class about that rule of 72? If you take 72 and you divided it by 1.24, you get 58 years. So we're actually pretty close with our estimate on that for the doubling time. But again, it's probably not that easy to be able to do 72 divided by 1.24 in your head, but it'll be approximately 56 years. Okay, we got a couple more examples left. This next one, what's the half-life? The half-life of plutonium is 13 years. Find the time for a 5-gram sample to decay to 1 gram. Okay, so let's just review. I know you've learned half-lives in different science classes. So what it means is this. If you have a 5-gram sample, then in 13 years from now, you'll have 2.5 grams. And in another 13 years from now, that's going to get halved. And in another 13 years from now, that's going to get halved. And in another 13 years from now, that's going to get halved. So for instance, if you had 2.5 grams after 13 years, you're going to have 1.25 grams after 26 years. And if you took half of that, you would get 0.625 grams after 39 years. And if you have that, you would get 0.3125. I might be off on that, grams after 52 years. But that's what's happening when you take the half-life of something. So the half-life span is 13 years. Every 13 years, you half what your remaining amount is. And so what they're saying is, can you now find the time it would take for 5 grams to reduce to 1 gram? Well, we could actually estimate something pretty good here, because if we know that there's a 1.25 grams after 26 years, then I'm going to predict that it would be somewhere around 30 years that you would have 1 gram left. So let's see what we could come up with this. Think about the form, and again, you could say, like, is there a half-life formula or not? I don't like to say that there's an exact formula. I like to just think, how could you create something based in these same growth and decay forms that we've been creating to be able to make something that would be able to work for us. So I wouldn't use it as a formula, but rather what's the form that we put this in. We begin with 5 grams, we end with 1. So this is what we start with, and this is what we end with. Our base is going to be 0.5, and that's because it's a half-life. And all half-life questions will have something like that. And it's going to do that every 13 years. And so if it does something like that every 13 years, then think about this, and this is going to be the hard part of a half-life question. We're going to say it is t over 13. Okay, and what that means is this. The top is going to represent the time elapsed. The bottom is going to represent the time to half-life. Okay. And so based off that, imagine what would happen if you had gone through 26 years. Well, if your numerator of your exponent was 26, then that would mean that you would have had 26 years have elapsed over the 13 years to half-life, and 26 over 13 is 2, so your exponent will be 2, meaning you'll have gone through 2 half-life cycles. You have to divide by 13 on your exponent, because that tells us how many times you have a half-life occurring. And in this case, we have a half-life occurring 2 times. So from there, we could take a look at what we have. I'm going to divide both sides by 5. And then once again here, depends. I don't know if you want to log both sides or if you want to put it in log form. Let's try putting it into log form from here. So log base of 0.5 of 1/5, you could say 0.2, equals your exponent, which is t over 13. And to isolate for t, you could times both sides by 13. and then we should be able to get our answer just like that. Again, you could have logged both sides as well, but let's see what we have here. So if we put this into our calculator, you get 30.2 years. Hey, our estimate of 30 was pretty bang on. So that's how you do a Half-Life question. Again, that part with the exponent is the tricky part, but hopefully the explanation makes sense for it. Okay, we have one final question here. So here's our question in terms of layers of glass. Okay, so this is some form of like tint that you can put on to be able to reduce the light that passes through. So each layer reduces light passing through by 5%. Let P of n represent the percent of light passing through each layer n. How many layers of glass are required for only 15% of light to be passed through? Okay, so if you have something like this, you begin with 100% light. You want to end with 15% light. And each layer makes everything reduce by an additional 5%, but it's not like it's 5% where then it would be, the next one would be 10% and 15%. It's not a linear relationship. This is an exponential relationship. So after your first layer is reduced by 5%, you're now reducing it by 5% of the remaining 95%. So it grows, it decays exponentially. And what that means is you have your full one and you subtract 5%. If you wanted to just write 0.95, you could, but basically you're retaining 95% of the light for n layers. So we divide by 100 and we get 0.15 equals 0.95 to the power of n. We put that from exponential form into log form. And then we put that into our calculator and we see what we end up with. And you get something like n equals 36.9857, blah, blah, blah. So that's basically saying 37 layers. Okay, so that's part 2. Nope, we have one more example. I skipped the gun on that. Okay, here we go. Let's look at something that has continuous decay. Okay, we could bring back the value of E for another question. A radioactive substance decays continuously according to the formula given here, where N is the final amount, C is the initial amount, and K is a constant, and T is the time in years. If 50 grams of a substance decays to 20 grams in 10 years, find the value of K to 4 decimal places. Let's see what we could say. We begin with 50 grams. It decays to 20 grams. And it does this in 10 years. Our time is 10, and we don't know what the value of K is. Let's divide both sides by 50 to try to isolate for our exponent as much as we can. 0.4 equals E to the 10K. You could ln both sides. I think I did that when we did those initial ln questions. Let's try something different this time. Let's put it in ln form. Ln of base E of 0.4 equals 10K. So then you could divide both sides by 10, divide both sides by 10, and K would be equal to, now if I have a base of E for ln, remember that's just like saying I have a log with a base of 10. It's presumed. So if you just write ln 0.4 over 10, you're in good shape. So let's give that a go, and we'll say ln 0.4 divided by 10, and we get something in which K is going to equal negative 0.0916. And that's 4 decimal places right there. Before you get started on the homework over here, these questions are good, but I would say probably um, let's have a discussion in the class and let's see sort of what's a good amount of work to do, because there's some great practice questions coming up, and we don't need to do both that and all the homework. So make sure you ask me in class before we get started on it. Thanks. Bye.